All right, let's get into it. Today, we're skipping the textbook theory, and we're getting our boots on the ground. We're going to walk through building a high-voltage substation, from the very first blueprint right up to the moment we flip that switch. This is all about how it gets done in the real world. So let's go. So here's our game plan. We've got 6 sections. We'll start with the basics, how the power actually moves. Then we'll meet the main equipment. After that, it's all about construction, safety, the crucial paperwork, and finally, the big moment, going live. Okay, section 1. First things first, let's figure out what a substation is actually doing. The best way to do that? Let's just follow the electricity on its journey through the system. So think of a substation like a huge, complex interchange on the electrical highway. You've got massive amounts of power zipping across the country on transmission lines at super high voltage. The substation's job is to grab that power, safely bring the voltage down, and then send it out to our local neighborhoods and businesses. Understanding this flow is absolutely key. Power comes in hot at 132,000 volts. Right away, it hits a bay of protective gear before it even gets to the main 132 kV bus bar. That's kind of like the central distribution hub. From there, it's directed into the massive power transformer, which does the heavy lifting, stepping it down to 33,000 volts. Finally, it hits another bus bar and gets sent out through underground feeder cables. That, in a nutshell, is the entire journey. Right, now that we know the path, let's meet the cast of characters. This is the heavy metal that makes everything we just talked about actually happen.
First step, the lightning arrestor. This thing is basically the substation's secret service agent. If a bolt of lightning hits a power line, we're talking a surge of 1,000,000 volts or more. This device acts like an instant escape hatch. It shunts all that dangerous energy straight into the ground in a split second, protecting all the expensive equipment down the line. It's a lifesaver, for sure.
Next up, the circuit breaker. And no, this is nothing like the one in your basement. Think of it as its bigger, way faster, and much, much more powerful cousin. Using things like SF6 gas or a vacuum, it can stop a massive electrical fault dead in its tracks in just milliseconds. If this thing fails, you could be looking at a widespread blackout. It's the absolute last line of defense between a small glitch and a total disaster. Now, isolators and earth switches. These are all about one thing, safety for the people doing the work. They are used to create a clear, visible air gap in a circuit, physically disconnecting it. Then the earth switch connects it to the ground. This guarantees a piece of equipment is totally de-energized and safe to touch. But here's the critical part. You can never open these when current is flowing.
And this slide just nails the difference. It's a super common and incredibly dangerous point of confusion out on site. A circuit breaker is built to work on load. It's designed to break a live circuit with huge amounts of current. An isolator is strictly offload. You only ever operate it after the circuit breaker has already done its job and killed the power. Mixing these two up is a recipe for a very, very bad day.
So how does the system even know when something's gone wrong? Well, it has senses, the instrument transformers. You've got current transformers, or CTs, and potential transformers, PTs. They take these huge, lethal currents and voltages and shrink them down to safe, readable levels. For instance, a CT might take 600 amps and turn it into a tiny 1 amp signal that a protection relay can safely read. That's the signal that tells the circuit breaker, hey, trip now.
And here it is, the heart of the entire substation, the power transformer. This beast of a machine is the whole reason we're here. It takes that incoming 132,000 volts from the transmission grid and, using the magic of electromagnetic induction, steps it all the way down to a more manageable 33,000 volts. This is the single most important job in the whole facility.
Okay, so we know what all the pieces are. Now let's get into the how. How do we actually take all this heavy metal off the truck and piece it together into a working substation? Getting the transformer in place is a massive job that requires some serious precision. It all starts with the concrete foundation. It has to be perfectly cured and level. Then the main tank, which weighs tons, is carefully craned into position. After that, thousands of liters of special insulating oil are pumped in and filtered. Only then can you start assembling all the external parts, like the bushings and cooling radiators, before finally connecting the main power cables. Now, getting the power out of the substation involves these heavy-duty underground cables. And let me tell you, it's a delicate process. You dig trenches, line them with soft sand to protect the cable, and then carefully lay the cable itself. Then comes the really skilled part, securing and sealing them at the switchgear, and then doing the terminations. Once it's all connected, you have to hit it with a high-voltage test to make absolutely sure it's perfect before it ever sees a real load.
Look, we can't talk about building anything, especially not a high-voltage site, without talking about the single most important thing. This isn't just a checkbox, it's the bedrock of every single thing we do.
So, I'm going to ask you, what do you think it is? Is it a crane? A high-tech tester? Nope. What's the one tool that absolutely ensures everyone gets to go home at the end of the day?
It's the work permit. It's just a piece of paper, but it is your official permission slip to work. It outlines the job, the risks, and the precautions. It's tied directly to lockout-tagout, which makes sure a system stays off, and proper grounding, which protects you from any stray energy. It's simple. You plan the work, and then you work the plan. Safety is the job.
Now, for every single thing you do on site, safely and correctly, there's a piece of paper to back it up. And trust me, this isn't just bureaucracy. This paper trail is the ultimate proof that you did the job right. Your Bible on site is going to be your drawings. You've got two main types. The single line diagram, or SLD, that's your electrical roadmap. It shows how everything is connected. Then you have the general arrangement, or GA drawing. That's your physical map. It tells you exactly where everything physically goes. You need both to know what you're doing. They're your site GPS. Okay, let's decode this alphabet soup of quality control, because you're going to see it everywhere. The ITP is your step-by-step quality checklist for a job. When you completed a step and it's ready for inspection, you raise a WIR. Now, if the inspector finds a problem, they'll issue an NCR, a non-conformance report, which means you have to fix it. Simple as that. And FAT and SAT? Those are just the tests that prove the gear worked at the factory and that it still works after we've installed it. And of course, there's a whole bunch of other critical documents. You'll have your official IFC drawings to build from, a bill of quantities to keep track of all your materials, and detailed method statements that spell out exactly how to do each task safely, all governed by the overall site HSE plan. All right, this is it, the moment of truth. We've built it, we've inspected it, we've documented it. Now it's time for the final, most critical phase, proving it all works and officially handing over the keys. And testing happens in two key stages. First is pre-commissioning. These are dead tests, meaning the main power is off. We're testing individual pieces of gear, checking insulation, making sure wires go to the right place, injecting signals into relays to see if they work. It's all about making sure the parts are good. Then comes final commissioning. This is when we do live tests. We start carefully energizing the system step by step to prove that everything works together as one complete integrated system. And remember this, the project is not done until the paperwork is done. The final handover package is the complete biography of the substation. It has the as-built drawings showing exactly what you built, all the final test reports, the manuals for how to operate and maintain everything, and of course, the golden ticket, the taking over certificate. This package is the final proof that the job was done right, done safely, and is ready to power our communities for decades.